Title of the module: Eigenvalue and Eigenvector Part 2. Dear learners, in the previous session we have learnt what is characteristic matrix, characteristic polynomial, characteristic equation, eigenvalue and eigenvectors of square matrices and its basic properties. Here we are going to find eigenvalues of some special matrices and some results related to these aspects. Let us see the definition of a similar matrices. First, we can see when two square matrices are related. Let A and B are n cross n matrices. The matrix A is related to B if there exists an invertible matrix Q such that A can be written as Q inverse B Q. So, if A and B are n cross n matrices and we can say A is related to B if we have to find a invertible matrix Q such that with the prescribed condition A equal to Q inverse B Q. When we identify the invertible matrix Q with this condition, we can say that A and B are related. Now, let us see some of the theorems related to these similar matrices. The first result is similar matrices have same eigenvalue and characteristic polynomial. So, two matrices are similar, they have eigenvalues are same as well as characteristic polynomials are same. Let us see the proof. Suppose A is similar to B. This is the matrix A and another matrix B, both are similar, are related. Okay. Now, there exists an invertible matrix as per our definition. There exists an invertible matrix Q such that A equal to Q inverse B Q. This is the definition of A and B are similar, that is A is related to B. Okay. Now, lambda the eigenvalue of A, and we are going to show that lambda is an eigenvalue of B because A and B are similar, matrices have same eigenvalues. We have to prove. I have taken lambda be an eigenvalue of A. I am going to prove that a lambda be an eigenvalue of B also. Okay. First, now we can take determinant, that is modulus of A minus lambda I equal to 0. Okay. Now, here instead of A we can supply B Q inverse B Q. How this will comes means lambda be an eigenvalue of A, that is modulus of A minus lambda I equal to 0. In other words, the determinant of, you can say. Okay. Q inverse B Q minus lambda, instead of I we can supply Q inverse Q. How it will come means already we can say that Q is an invertible matrix. Therefore, Q inverse Q this is an identity matrix. So, instead of I we can write lambda Q inverse of Q. Now, determinant of Q inverse we can take B minus lambda outside and Q here common, this value becomes 0. So, this can be rewritten as determinant of Q inverse and B minus lambda I as well as the determinant of Q equal to 0. See, Q is an invertible matrix as well as determinant of Q the whole inverse equal to determinant of Q inverse. We can supply these two things here and we can get that B minus lambda I equal to 0. So, this shows that the characteristic polynomial of B is same as the characteristic polynomial of A, and this shows that lambda is an eigenvalue of A as well as lambda is an eigenvalue of B. So, similar matrices have same eigenvalue as well as characteristic polynomial. I have just proved this result. Now, another result, lambda 1, lambda 2, lambda n are finite eigenvalues of A, then 1 by lambda, they are reciprocal, 1 by lambda, 1 by lambda 1, 1 by lambda 2 and 1 by lambda n are eigenvalues of 1 by A, that is nothing but A inverse. So, here A is an invertible matrix. So, lambda I or the eigenvalues of A, we are going to show that lambda I inverse are eigenvalues of A inverse. Let us see the proof. Let lambda be an eigenvalue of A. As per the definition, Ax equal to lambda x for some non-zero vector x. Now, here A is invertible, so we can write here Ax equal to lambda x, you can pre-multiply by A inverse. So, here A inverse A, you can take identity and here, so the value becomes x, and here A inverse lambda can be written as lambda A inverse. Therefore, x equal to lambda A inverse x. This lambda comes here, therefore, the value of this lambda comes here, means this is 1 by lambda into x equal to A inverse lambda. So, here 1 by lambda x equal to A inverse. See here, lambda be an eigenvalue of A means Ax equal to lambda x. Here instead of A inverse, instead of lambda, 1 by lambda. So, this shows that 1 by lambda is an eigenvalue of A inverse. That is all. So, this is a particular value of lambda. So, we can prove it for generalized, or we can prove it or generalize for finite values. Therefore, 1 by lambda 1, 1 by lambda 2 up to 1 by lambda n are eigenvalues of A inverse. So, first we have proved that similar matrix has same eigenvalues and same characteristic polynomial. In the second one, we have proved that lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of lambda A inverse. The third result is eigenvalues of a Hermitian matrix are real. So, now we are going to prove that the eigenvalues of a Hermitian matrix are real. So, when we can say that a matrix is Hermitian. So, this is a matrix A I have taken. This matrix is Hermitian means A star equal to A. Here star indicates conjugate transpose. Star indicates conjugate transpose. So, what is mean by conjugate transpose? See here, A bar transpose equal to A. So, A star is nothing but A bar transpose. So, a matrix A is Hermitian, A bar transpose equal to A. That is A star equal to A. Now, we are going to show that this matrix have eigenvalues, that eigenvalues are real. So, we have taken lambda is an eigenvalue of this Hermitian matrix, that lambda is real, that is all. So, we are going to show that lambda is real. For that, lambda is an eigenvalue, A is an Hermitian matrix. As per the definition of a Hermitian matrix, A star equal to A, and lambda is an eigenvalue of A means Ax equal to lambda x for some non-zero vector x. Then Ax equal to lambda x, this is the condition. We can apply star conjugate transpose, that is all. Conjugate transpose on both sides, Ax star equal to lambda x star. So, this can be written as per the definition of conjugate transpose, x star A star equal to x star lambda star. Now, again x star lambda star equal to x star lambda bar. We know that lambda star equal to lambda bar. Now, x star A star x equal to x star lambda bar x. I have post multiply by x, that is all. This is the value already given, post multiply by this by x. Okay. Now, instead of A star, we can supply A. Why? Because A is a Hermitian matrix. A is a Hermitian matrix means A star equal to A. So, x star instead of A star A, x star Ax equal to, here I can rearrange, shuffle the order, A lambda bar x star x. Here instead of Ax, I have supply A lambda x, because lambda is an eigenvalue of A, Ax equal to lambda x. So, instead of Ax, we have supply lambda x. Now, x star lambda x equal to lambda bar x star x. Here x star x can be regrouped and this can be written as lambda x star x equal to lambda bar x star x. Now, we can take this thing in this side. So, this can be written as x star x lambda minus lambda bar x star x equal to 0. X star x we can take commonly outside, then lambda minus lambda bar into x star x equal to 0. We know that x star x not equal to 0. So, the only way is lambda minus lambda bar equal to 0, because these two things their product is 0, this is non-zero. So, what is the way? So, the only way is lambda minus lambda bar equal to 0. Lambda minus lambda bar equal to 0 indicates lambda equal to lambda bar. So, their conjugate and lambda and their the conjugate of lambda are both are equal, that means lambda is real. So, eigenvalues of a Hermitian matrix are real, because I have taken lambda is an eigenvalue of a Hermitian matrix A. I have proved that lambda equal to lambda bar shows that lambda is real. So, this is the third result. And now, we are going to define another matrix, that is Hugh Hermitian. We already know that the matrix is Hugh Hermitian. that is A star equal to A minus A. See, Hermitian matrix A star equal to A and skew Hermitian matrix A star equal to minus A. In other words, A bar transpose equal to minus A. Now, we are going to show that eigenvalues of skew Hermitian matrix are 0 or purely imaginary. So, whenever I will take a matrix A that is skew Hermitian, lambda be an eigenvalue of A. So, I am going to show that either lambda equal to 0 or lambda is purely imaginary. That is all. Let us start the proof. A be a skew Hermitian matrix. What is skew Hermitian matrix? A star equal to minus A. What is star indicates? Conjugate transpose. That means A bar transpose equal to minus A. Now, A star equal to minus A, this is the definition of skew Hermitian matrix, and Ax equal to lambda. Guess how it will come? Lambda is an eigenvalue. Now, I am taking conjugate transpose on both sides, that is Ax transpose, Ax conjugate, that is bar equal to lambda x bar. According to the property of this star, we can write x star A star equal to x star lambda star. And here x star lambda star equal to x star lambda bar. I already told lambda star equal to lambda bar. Now, x star A star x equal to x star lambda bar x. How it will comes? I can post multiply by x because x is non-zero. We can post multiply. Now, instead of A star, I can supply minus A because A is skew Hermitian. So, minus x star Ax equal to lambda bar x star x. Here I can shuffle again Ax equal to lambda x because lambda is an eigenvalue. So, minus x star lambda x equal to lambda bar x star x. Here we can write x star x into lambda minus lambda, and here x star x into lambda bar. We can take this here. So, it will come in this side as my negative sign. Therefore, minus lambda bar into x star x equal to 0. As in the previous theorem, we have mentioned that x star x non-zero. So, what is the only way? Minus lambda star equal to 0, lambda bar equal to. So, taking minus outside, lambda plus lambda bar equal to 0. This shows that lambda plus lambda bar equal to 0. This shows that 2 into real part of lambda. We know that for any number lambda plus their conjugate, we can add these two numbers and divided by 2, you can get the real part of that number. So, this shows that 2 into real part of lambda equal to 0. 2 into real part of lambda equal to 0 shows that lambda is either 0 or purely imaginary, because real part of lambda equal to 0, that means the number is purely imaginary. That is all. So, this shows that eigenvalues of skew Hermitian matrix are 0 or purely imaginary. Now, in the second theorem, we have shown that the eigenvalues of Hermitian matrix, and the third one we have shown that again eigenvalues of skew Hermitian matrix. Now, we are going to show that the eigenvalues of unitary matrix of the nature. So, when we say that a matrix is a unitary matrix, this is the definition of a unitary matrix. A matrix A is said to be unitary, A star A, that is again shows that star stands for conjugate transpose. So, A star A equal to A star equal to I. This shows that the matrix is unitary. Now, we are going to show that the eigenvalues of the unitary matrix are unit modulus. That means, whenever I will take a eigenvalue lambda, so lambda is an eigenvalue of a unitary matrix, I am going to show that the modulus of lambda equal to 1, that is all. Unit modulus means modulus of lambda equal to 1. So, A unitary matrix, lambda eigenvalue of A, the condition for unitary matrix here, A star equal to A star A equal to I. The condition for eigenvalue is here, Ax equal to lambda x. I have taken the conjugate transpose on both sides, Ax star equal to lambda x star. Again, the same procedure prescribed in the above two theorems. This can be written as x star A star equal to x star lambda star. Instead of lambda star, we can write lambda bar. And I have pre-multiplied both sides by Ax. Here I have written Ax. So, this is because A is a unitary matrix. So, what is the condition for a unitary? A star A equal to identity. Therefore, instead of A star A, we can write I. Therefore, x star Ix equal to x star lambda bar. Instead of Ax, we can write lambda x. Now, I is the identity transformation. So, it maps any element to that element itself. Therefore, Ix equal to x. Now, x star x equal to x star lambda bar lambda x. Here again I have rewritten x star and xi combinedly written this, and come this one to this side, this can be written as 1 minus lambda bar lambda into x star x equal to 0, because x star x not equal to 0, again the only way is 1 minus lambda bar lambda equal to 0. So, 1 minus lambda lambda bar is nothing but modulus lambda square equal to 0, 1 minus modulus lambda square equal to 0. 1 minus lambda square equal to 0 means modulus lambda square equal to 1. Modulus lambda square equal to 1 means the only possibilities is modulus lambda equal to 1. That is the eigenvalue, because lambda is an eigenvalue. The eigenvalue of a unitary matrix have unit modulus. So, let us see some more result in detail. This result 6 shows the eigenvalues of an idempotent matrix. Eigenvalues of an idempotent matrix are 0 and 1. We are going to prove. Let A be an idempotent matrix. As per the definition of an idempotent matrix, A square equal to A. Suppose lambda is an eigenvalue of A. Then Ax equal to lambda x for some non-zero vector x. Now, A square equal to A. Y means idempotent matrix A. So, we can post multiply both sides by x, that is A square x equal to Ax. Now, A square x again can be written as Ax equal to Ax. Since Ax equal to lambda x, we can supply Ax equal to lambda x, therefore, A lambda x equal to lambda x. We can rearrange the terms A and lambda, because lambda is a scalar, therefore, which implies lambda Ax equal to lambda x. Now, again we can substitute Ax equal to lambda x, which implies lambda x equal to lambda x. So, lambda this is nothing but lambda square x equal to lambda x, which implies lambda square equal to lambda, because x is non-zero. Therefore, lambda square minus lambda equal to 0. We can take lambda outside. Therefore, lambda into lambda minus 1 equal to 0, which implies lambda equal to 0, 1. Thus, the eigenvalues of an idempotent matrix are 0 and 1 itself. Result 7. Eigenvalues of a real orthogonal matrix are plus 1 and minus 1, that is plus or minus 1. Now, let us see when a matrix is orthogonal. A matrix A is orthogonal if A transpose equal to A transpose A equal to I. Already we studied the unitary matrix, these two are similar matrices. There A star equal to A star A equal to I. Here A transpose equal to A transpose A equal to I, where A transpose is the transpose of a matrix A and as well as I is the identity matrix. Let A be a orthogonal matrix with the eigenvalue lambda. So, what is the definition of an orthogonal matrix? A transpose equal to A transpose A equal to I. What is the definition of eigenvalue lambda? Ax equal to lambda x for some non-zero vector x. Now, Ax equal to lambda x, I can take transpose on both sides, that is Ax transpose equal to lambda x transpose. Now, according to the property of transpose, we can write Ax transpose as x transpose A transpose, lambda x transpose as x transpose lambda transpose, which implies x transpose A transpose Ax equal to x transpose lambda Ax. What I have made here? Just I have post multiply by Ax. Now, instead of A transpose A, you can apply I. Therefore, x transpose Ix equal to x transpose. Instead of x transpose, I can supply again here x transpose lambda Ax. Next one, Ix is the I is the identity transformation. Therefore, Ix equal to x. Now, x transpose x equal to x transpose lambda x. Here, instead of Ax, I can supply lambda x. Here, x transpose x equal to x transpose x lambda square. So, x transpose x not equal to 0. So, the only possibility is 1 minus lambda square equal to 0. 1 minus lambda square equal to 0 means lambda square equal to 1. Lambda square equal to 1 implies that lambda equal to plus or minus 1. Therefore, in this orthogonal matrix, the eigenvalues are plus or minus 1. So, the eigenvalues are already proved in this orthogonal matrix are plus or minus 1. Now, let us see the result 8. The eigenvalues of an involutory matrix are plus or minus 1. So, now what do you mean by involutory matrix? Let A be an involutory matrix, that means A square equal to identity. Already we have seen idempotent matrix, that is A square equal to A, here A square equal to I. Now, we are going to prove this. Suppose lambda is an eigenvalue of A, then Ax equal to lambda x is a non-zero vector. According to our assumption, A is an involutory matrix, therefore, A square equal to I. Again we have here we can post multiply by x, therefore, A square equal to A ix. A square can be written as A ax equal to ix. Instead of Ax we can supply lambda x, therefore, A lambda x equal to Ix equal to x. Again we can rearrange the term, lambda is a scalar, therefore, lambda Ax equal to x. Instead of Ax again supply lambda x, therefore, lambda x equal to x. So, this is true for every x, therefore, lambda square equal to 1. So, lambda square equal to 1 means lambda equal to plus or minus 1. That is, the eigenvalues of an involutory matrix are plus or minus 1. Let us see another result. The matrix A and A transpose has same eigenvalues. This result provide a very good opportunity for other theorems and other sums. So, let us see the importance of this theorem. So, it is known that determinant of A equal to determinant of A transpose. Also, if lambda is an eigenvalue of A, then we can write modulus of A minus lambda A equal to 0. Modulus of A minus lambda A equal to 0 implies modulus of A minus lambda A transpose equal to 0, because A modulus of A equal to modulus of A transpose. So, here apply the properties of transpose. A minus lambda I transpose can be written as A transpose minus lambda into I transpose equal to 0. Then A transpose minus I transpose is nothing but I, therefore, A transpose minus lambda I equal to 0. Therefore, lambda is an eigenvalue of A transpose. If lambda is an eigenvalue of A, then lambda is an eigenvalue of A transpose also. Next result is, if lambda is an eigenvalue of A, then the eigenvalue of A minus ki for any scalar k is lambda minus k. So, which is the generalization. It is known that lambda is an eigenvalue of A, then Ax equal to lambda x. So, instead of A, we can supply here A minus ki of x, we are going to evaluate this. This can be written as Ax minus kix, but I is the identity transformation, therefore, this can be written as Ax minus kx. Instead of Ax, lambda x. So, lambda x minus kx, take it x commonly outside, therefore, lambda minus k into x. So, lambda minus k is an eigenvalue of A minus ki. In this session, we have learned detailed about the eigenvalue of some special matrices and its properties, and some results related to these aspects. Hope you have learned the eigenvalues of Hermitian matrix, Hugh Hermitian matrix, unitary matrix, involutory matrix and transpose matrices. So, you have a better idea of eigenvalues of various matrices. For better understanding, do some more sums given in this script. Thank you.